Good morning all. Today we will going to study about the number system. The objectives are for the number system are understand why computer use binary base 2 numbering, understand how to convert base 2 numbers to base 10 or base 8, understand how to convert base 8 numbers to base 10 or base 2, understand how to convert base 16 numbers, that is hexadecimal numbers, to base 10, that is a decimal number system, and then to binary number system, and then to octal number system. Now, why binary system is needed? Since we know that computers are made of a series of switches and each switch has two states. It is either on or off. Each state can be represented by a number 1 for on and 0 for off. Now the conversion process from binary system to decimal number system will be as shown by the slide or as shown by the example. In case of like 10011, we can say that in case of 1 it is on, in case of 0 it is off, again it is off, then on, and so on, again it is on. So we gradually put 2 to the power the state, that is for 1 starting from rightmost digit 2 to the power 0, then 2 to the power 1, then 2 to the power 2, then 2 to the power 3, and then 2 to the power 4. We can write it in the exponential manner, and then corresponding weights will be calculated. We can skip the digits for which the state is off, that is in case of 0 we will omit that particular exponent number or that particular exponent value, and then we will calculate the rest ones by summing them up. For on state we will count the value 2 to the power 0, then again for 1 2 to the power 1 will be counted, then for 0 we will skip the 2 to the power 2 value, then again for 0 we will again skip 2 to the power 3 value, then again the state is on, so we will consider 2 to the power 4. So summing up them, we will get the calculation as 16 plus 0 plus 0 plus 2 plus 1, that is the conversion is 19, and it will be quoted in the parenthesis, and outer the parenthesis we will put the base of the number system, that is 10. So the conversion of 10011 in the decimal number system is 19. Number system includes decimal, prime, binary, octal, and hexadecimal. Each system have 4 number base. Number system base symbol. In case of binary, the base is 2, the symbol is B. In case of octal number system, the base is 8, and for decimal number system it is 10, and for hexadecimal number system it is 16. The symbols are for octal it is O, for decimal it is D, and for hexadecimal it is H. Moving further, let's consider the decimal number system. The decimal number system uses base 10. It includes the digit from 0 to 9. We will always keep the digits less than 1 from the base value, that is for in case of decimal number system the base is 10, so we will keep the values from starting from 0 to n minus 1, where n is the base of the system, 10 minus 1. So in case of decimal number system it will be up to 9. So the weighted values for each positions are they are shown in the figure. They are for integer part we will cover up the digits by putting the weights as base to the power position. So 10 to the power 0, then 10 to the power 1, 10 to the power 2, 10 to the power 3, and so on, where 10 is the base of the system. Then for decimal part we will cover up the weights as 10 to the power minus 1, 10 to the power minus 2, then 10 to the power minus 3, and so on. Each digit appearing to the left of the decimal point represents a value between 0 and 9. Power of 10 represented by its position in the number. Digits appearing to the right of decimal point represent a value between 0 and 9 and increasing negative power of 10. For example, let's take an example. If we wish to convert 725.194 and we wish to write it down in the weighted position system, then we can cover up as 725 first, it is the integer part of the number, so we will write it as 7 into 10 to the power 2, then plus 2 into 10 to the power 1 plus 5 into 10 to the power 0. This is the expanded form we have studied in our maybe in the second or third class, where we basically study about the representing a particular number, unit, tens, 100, 1000, so on, in that particular format. Place value, face value, we have studied in our class 2 or class 3. So it is represented as 700 plus 20 plus 5. So it will be 725. Then for 0.194, we will basically start from the 10 to the power minus 1 position. So 1 into 10 to the power minus 1 plus 9 into 10 to the power minus 2 plus 4 into 10 to the power minus 3. In the expanded form, it will be 0.1 plus 0.09 plus 0.004. So summing up them, we will get our number 725 plus 194. In case of binary system, the procedure is similar. Most modern computer system using binary logic, the computer requires to present a particular value in the format 0 or 1 using two voltage levels, where basically we will cover the logic 0 by using the 0 volt, and logic 1 will be basically indicated by plus 5 volt or the higher value of the voltage. The binary number system uses base 2, which includes only the digits 0 and 1. The weighted values for each positions are like in case of a decimal number system. Here again we will start the integer part by keeping the place values 2 to the power 1, 2 to the power 2, 2 to the power 3, and so on. And for fractional part, we will cover up by keeping the place or position on the 2 to the power, and we will start from minus 1, minus 2, and so on. So it has written over there. For integer part, we will start the values, or the weighted values will be basically calculated by multiplying 2 to the power 0, the particular digit, then 2 to the power 2 as per the position of a particular number. Then the weights are 1, 2, 4, 8, 16, 32, and so on. And in case of fractional part, it will be covered as 0.5, 0.25, and so on. Number base conversion. Binary to decimal number conversion can be done by multiplying each digit by its weighted position and each of the weighted values together, or use expansion form directly. For example, if I wish to convert 1100 1010, then it will be represented as 1 into 2 to the power 7, then plus 1 into 2 to the power 6, plus 0 into 2 to the power 5, plus 0 into 2 to the power 4, plus 1 into 2 to the power 3, plus 0 into 2 to the power 2, plus 1 into 2 to the power 1, plus 0 into 2 to the power 0. Whenever we basically sum up these values, or we basically sum up the weighted numbers, then we will get the answer as 202. There are two methods that may be used to convert from integer number to decimal form to binary form. First is, it can be done by repeated division by 2. In this method, we divide the decimal number by 2, and the remainder will be either 0 or 1, which will be noted down on the right side of the particular column, which we will going to see in the examples later on. If the remainder is 1, write down a 1. When performing the division, the remainders, which will represent the binary equivalent of the decimal number, are written beginning at the least significant digit, and each new digit is written to most significant digit the left of. For example, if I wish to convert the number 333 to binary, then I usually divide 333 by 2 up till when the remainder portion comes to a particular 0 value. So at first step, we will divide 333 by 2, then the quotient will be 166 and the remainder will be 1, and this will be the binary equivalent or the digit we have to quote in the binary representation. Then the Question will be now divided by 2, and this process will be continued till in the question column we get a 0. So 166 divided by 2, we will get new question test 83, and the remainder will be 0, because the number is 166 is completely divisible by 2. Then the new question test or the new number which we have to divide by 2 is 83. Then we will divide by 2, then the question will be 41 and remainder will be 1. Moving up to last column, we will get 1 by 2, then the question will be 0 and remainder will be 1. Here we will stop as the question is 0. So if we again divide this by 2, we will definitely going to have a 0 remainder continuously. So we will stop our process whenever we get a question 0. Then in case we wish to write the converted number or the converted expression for 333 in the binary system, the last column will indicate the appropriate conversion, which is coming as 10 100 110 and 1. We can check by the weighted position system, and is it the conversion is completed or not. Next, moving towards the octal number system. Computer scientists are often looking for shortcuts to do things. So for the paperwork, we basically defined a new system of conversion of number system, so that the procedure will be gradually shortened. One of the ways in which we can represent binary numbers is to use their octal equivalents instead. This is especially helpful when we use to do fairly complicated tasks using numbers. The octal numbering system includes 8 base digits, which is starting from 0 to 7. After 7, the next placeholder to the right begins with a 1. So in case of octal number system, if you wish to represent our numbers, decimal numbers, then we will write as 0 1 2 3 4 5 6 and 7, and after 7 the base 8 will be written as 10. Then the numbers 9 in the decimal system will be written as 11 12 13 14 15, and for 16 we will get the converted system or the converted number is 20. The process of conversion in the octal system is similar to that we have performed in the binary number system. That is, we are using the conversion process from decimal to binary can be utilized in the conversion from decimal to octal number system also. Here the representation technique is similar to that we have utilized in the binary number system. First of all, we have to indicate the places that will be indicated by 1 2 3 and so on, and then the place values will be based to the power position or the place. That is here in case of octal number system the base is 8, and again we will start the integer number system from considering the place as a 0, then 1 2 3 4 and so on. So the weighted values will be basically 8 to the power 0 is 1, 8 to the power 1 is 8, then 8 to the power 2 is 64. So in case of octal number system, the values will come out, or the weights will come out as 1 8 64 and so on. If you wish to take an example of transformation of a decimal number to octal number system, again the procedure is similar as I have already earlier said, that here we have to divide the decimal number by the base of the system, that is 8, successively, and again we have to note it down the quotient, remainder and the converted version. So let's take the example of 44978. It is a decimal number and we have to convert it into the octal system. So the division by 8 will give you quotient as 5622, the remainder is 2. Here 2 is allowed because in octal number system we basically cover up the digits from 0 to 7. So 2 is allowed. Then a new portion which we have to divide by 8 is 5622. It can be taken from the quotient column. So 5622 divided by 8, we will get 702. The remainder is 6. It will be quoted down in the reverse fashion. 702 by 8, 87, 6. then so on up till whenever we will get in the question column 0, we will stop our process, like whatever we have done in the binary number system. So 1 by 8, the question will be 0 and the remainder is 1, and the binary or the equivalent number representation of 44978 is 127662. So thank you so much for watching my video. Keep connected with me. In next class, I will basically cover up the conversion from binary to octal and octal to binary. So thanks for watching.